So thank you very much again for the invitation. And so I'll talk about challenges and solutions in modeling laser plasma accelerators. And this is a teamwork, of course. I'm the speaker, but this work from the entire WarpX team. So the outline, I will first introduce the challenges in modeling of plasma accelerators, and in particular the main challenge in range and of space and time scales and some solutions. I will then introduce the WarpX and the DOE Exascale Computing Project, talk about the advanced algorithms that we have been developing, then show some application to the modeling of chains of plasma accelerator stages, discuss a bit in situ data analysis and visualization, and then I will summarize. Okay. Fine. Okay, so first on the modeling of plasma accelerators. So backtrack a little bit on plasma, the charged particle generation and acceleration via laser plasma interaction. There are a number of different ways to do it, and depending largely on the density of the plasma. So starting with underdense plasma, you can drive a laser or particle beam into a plasma column, and that creates a wake with an intense electric field that you can use to accelerate efficiently some electrons or positron beams. And main applications are in high energy physics, potentially colliders and light sources. Then you can instead, with the higher density plasma, have some absorption transmission, and then generate and accelerate some proton or ion beams. This way, some application could be cancer hadron therapy, proton radiography, and more. And then with higher density, even you have reflection of the laser and so-called plasma mirrors that you can use to generate some attosecond light sources or electron beam, and that with some possible application also to high field physics. So we will focus on the first one in this talk. Plasma accelerators can make particle accelerators smaller. As you know, it started small. We see here Lorentz particle accelerator in his hand in 1930. The largest now, as we all know, is the LHC at CERN. And that getting to the next step with potentially larger accelerators can be very costly. The consumption can be very big. So there's definitely incentive to make them smaller and of course possible cheaper. So one possible way is plasma acceleration, again using either laser beam or particle beam as the driver. And the other advantages is that they offer orders of magnitude larger accelerating gradients. And if going forward, potentially proposing colliders, say electron-positron colliders in the 1 to 30 TeV range to be interesting in the physics, then that would translate to from tens to thousands of laser wake field accelerator stages, with each stage at the 5 to 10 GeV per stage due to some physics consideration that have been discussed already. I will not go into that, but similarly, there's some possibility with beam-driven that require also some staging. Okay, right. So plasma accelerators are challenging to model. So on the simulation side, what makes it difficult is that there's a short driver. So you see, hopefully, that's going through Zoom, little animation here with a small driver in red that creates the wake, propagates through a very long plasma. And so that means many, many time steps in order to do this physics right. And at the same time, you see here, this is a snapshot from a simulation from Carlo Benedetti. You see very, very small feature, whether it's the driver itself or the structures in the wake, that translate to many grid cells and microparticles. So there's two methods that have been developed to reduce the number of time steps in particular. The first one is the oldest one, is the quasi-static approximation that works on separation of fast and slow moving scale. So the driver, whether the laser or the particle beam, they are very stiff. And so that long space and time scales, you can push them less often with the large time step, while on the other hand, the plasma electrons and to some extent the protons, they are very mobile and respond to very short space and time scale, and that you use to push them separately. So you treat the beams and plasma separately. I will not go through the detail because we'll focus on the second method. But this is basically the gist of the method here. So this approximation neglects electromagnetic wave propagation and retardation, cannot model trapping without some extra trick, and laser is being modeled using the envelope approximation with this approximation. So the second methods that we'll discuss in more detail is the so-called Lorentz boosted frame method, which simply is the selection of a reference of frame that minimizes the space and time range scale. So using Lorentz dilation, contraction of space and time to do this. This preserves electromagnetic wave propagation, retardation, and trapping. I mean, for the wave propagation, of course, as long as this is supported by the grid. And as the laser is modeled either directly or with envelope approximation. So the gist of the optimal reference frame to bridge space and time scale is like this. If you look in the lab frame, you have a very long plasma at rest and say a laser beam with a very short wavelength. And the number of time steps that you need to do the simulation for the laser to cross the plasma is proportional to the length of plasma divided by the wavelength of the laser. That's translate many time steps. If now you choose a boosted frame that goes at velocity with a relativistic factor gamma, you now have contraction of the plasma by the gamma factor, dilation of the laser wavelength by gamma times 1 plus beta, and the number of time steps are now the ratio of the new length of the plasma divided by the new wavelength of the laser. So if you do the comparison now of your number of time steps in the boosted frame compared to the lab frame, you have a factor gamma squared times 1 plus beta. So say that you take a frame of gamma equal 100 that correspond to a speed up of more than 10,000. And with this little animation that shows you how that works, basically is you have the simulation in the lab frame on the left, and equivalently the crossing on the right is much faster, and that's just an illustration of what happens. So now there's a price to pay. The physics looks different in the boosted frame and the lab frame. So you need to transform between boost and lab frame, and I'll say more about that. And after that, I'll also say more about the numerical Cherenkov instability that occurs because now the plasma is drifted compared to the grid, and we'll talk more about this. So first on we need to ensure frame independent initial conditions. So the way that it is being done is it's usually easy in the lab frame to know the particle beam or laser beam condition at a given plane. And so it's not hard to transform this data from the lab frame to the boosted frame and inject the particle through that plane. So that plane which is fixed in the lab frame becomes moving backward. In the boosted frame, you inject your particle so they become alive. When they cross this plane, this is where they start to acquire some color in that plot. While for the antenna, it's basically just a vertical antenna that moves in front of the plasma and injects the laser into the plasma. And this way you have independent simulation that will give the same result independently on the frame. But now one need to look at the output, and that can look fairly different. You see the top here is a simulation of a laser plasma acceleration in the lab frame. Looks very familiar with the laser, the wake, the accelerated beam. Now the equivalent simulation in the boosted frame, as you will see, looks fairly different. And one way to understand the difference is to look at the laser on axis and its time evolution, and compare that to what happens in the boosted frame, where eventually, for a given frame, you have so-called hyperbolic rotation of your axis. And what it does is that this laser stripe that looks like this in the lab frame here, that's moving with the wake, they may align, perpendicular to the time axis. And that means that this spatial oscillation of the laser, they transform the time beating in the plasma in the boosted frame. So it looks very unintuitive, but it's actually the same physics. And we can see the little animation. You see the simulation in the lab frame at the top. I hope it's going well through Zoom. And as you can see, same simulation, same physics, and that's been checked in the bottom. At the bottom, that looks very different. So there's some additional module that does take the simulation from the boosted frame, translate that to the lab frame, and that has been implemented to various codes. So number of codes have been implemented to look at plasma accelerators, whether it's laser driven or beam driven, and they use one of the two techniques, and you see a number of codes that have been implementing the quasi-static technique, and another number of codes that have been implementing the boosted frame PIC technique, and we'll focus on the WarpX code, which is our latest development in the team. So I will move now to the introduction of the code, which is part of the DOE Exascale Computing Project. And first, maybe just a bit of history, because some people often ask, okay, there's this code warp that has existed for some time that's been used for plasma acceleration. Also, what's the relationship to WarpX? So WarpX is basically the new version of warp, at least for an electromagnetic PIC. So warp was a code started in 1989 by Alex Friedman and collaborators, and is a Fortran code with a Python layer. Around 2013 or so, as part of the pre-Exascale programs at NERSC, the NASA program at Berkeley Lab, we started optimizing some of the warp routines that we've externalized into a library that we call Pixar, and that gives a boost for the simulation of plasma acceleration with warp plus Pixar. And then a new project started, the Exascale project started, which I will present next. And then we started this new code, WarpX, that's very much started as with warp plus Pixar, and then became this new C++ code based on AMRX and adaptive mesh refinement library, and runs on both CPUs and GPUs efficiently. So again, WarpX is part of the Exascale Computing Project, which is a very, very big project at DOE. And the key things to note as far as this presentation is concerned is that it includes both the procurement of the machines, so a number of Exascale supercomputer will be available in the US starting next year for full access, for at least for some of them. And in addition to the hardware, it's developing the software complete stack, starting from compilers up to physics application. And 21 applications were selected across the DOE science range of possibilities. And the WarpX project was selected. So the goal of the WarpX project is to develop a tool for exascale modeling of advanced particle accelerators. The challenge problem, which is to be reached in 2023, is to enable convergence studies in 3D of tens of consecutive multi-GeV stages for laser and beam-driven plasma accelerators. So how we're doing this is, again, we have this new code WarpX. in which we combine the most advanced algorithms and port to emerging architectures. So that means many core, but especially now in the US, that means GPUs. And we do this with a team from Berkeley Labs, Slack, and Livermore. And I will say more about this shortly. The WarpX leverages, extensively the AMRX, which is a library for adaptive mesh refinement technology, which provides a lot of capabilities that then the WarpX team does not need to handle by itself. So the AMRX library provides the data structures, domain decomposition, MPI communications, load balancing, mesh refinement, and also the means to write the code once in a portable way for GPU, CPU, formerly for KNL, all these targets. And the WarpX code base, which is what we care more on the laser plasma accelerator modeling side, is we orchestrate the particle in cell loop. We provide low-level particle in cell kernels for current deposition, particle pusher, field solver, field gather. So again, all written using the MRX library capabilities. We also provide additional modules like ionization and QED. The last one being in collaboration with our colleagues from CEA. Exactly. So here's what the WarpX software stack looks like at the moment. So again, the WarpX implement the physics routines, the rack solver application logic based on MRX. There's additional module for all the diagnostics, data visualization and analysis that is relatively complex, as you see on the left. Then there's, when needed, we use additional math solvers plus additional physics solvers. So like the QED module, for example, sits in this box here. And all of this is built on top of the MPI, CUDA, OpenMP, etc. So again, all of this is handled by MRX and so is somewhat hidden to the WarpX team here, and that's a very nice feature. So this package is handled by a package manager that enables a compilation with automatic testing on Linux, OS 10, Windows operating system. And there's also an optional Python layer for steering of the code and interactivity that is quite nice. So as I mentioned, the code is developed by a team that you see here, which is multidisciplinary and multi-institutions, with physicists from the Accelerator division at Berkeley Lab, that came a bit too quick, as well as from Livermore Lab and Slack, as well as applied mathematicians and computer scientists, both from the Accelerator division and from the computational division and the Nurse Computer Center at Berkeley Lab. In addition, we have a number of collaborators, a growing list from CEA, DESI, and recently also a PhD from a student from Sir Lorenzo Giacomo, who's starting to participate in the development. So many advanced algorithms are needed to reach our goal. I've already mentioned the Lorentz, boosted transform in order to lower the number of time steps. Beyond this, in order to reach higher accuracy, we are developing mesh refinement, ultimately adaptive. So this is where the MRX library, of course, is very useful to us. Still for higher accuracy, I will talk a bit more about spectral, that is FFT-based Maxwell solvers. So not just finite difference solvers as usual in PIC codes. For higher stability, we have a way to suppress numerical Cherenkov instability. So I will detail those a bit more. And for higher scalability, we do FFTs on local subdomains, not just on the full grid. I'll say more about this. And for lower dimensionality and reduced physics, we also have options for axisymmetric solvers with azimuthal Fourier decomposition. And we also plan to add envelopes laser solver to the mix. So back to the high accuracy with adaptive mesh refinement. So mesh refinement is fairly widespread in some other domain, like in fluid dynamics, for example. Not that widespread with PIC, especially electromagnetic PIC simulation. And the reason for that is that there's some extra complication, number of things to be careful at. So mesh refinement means that there's a jump of resolution from, say, a refinement area here in the center of the grid and the main grid here. And things that could happen because you kind of break the symmetry here, jump resolution, for a particle that come here close to this boundary between the two resolution, you can see some spurious self-forces that arise. You can also have some wave reflections. If you think about it, if you have an electromagnetic wave that is resolved by the fine grid, but not by the coarser grid, then what happens to it at the boundary? And if you just try to stitch with some interpolation, it's usually reflected with actually some amplifications. It can become very quickly unstable. And you can have some dispersion mismatch. Numerical dispersion can be different between the fine grid and the coarser grid. That leads to potential reflection too. So I will not go into too many details there, but we've developed an algorithm that basically decoupled what happens with the fine grids and the coarse grids and avoid stitching the Maxwell solutions by interpolation by a substitution method where we actually solve the fields independently on the fine grid patch and another coarse grid patch and use the linearity of Maxwell's equations to basically, when we compute the force, which includes both the electromagnetic and magnetic forces in there, we basically take the field that encompasses the source terms from particles both outside and inside the refined area. And then we subtract what's happening in the coarse patch and add what's happening in the fine patch. And so that's why it's called a substitution. Basically, you kind of remove what's happening at the coarse level, the main grid with the coarse patch, and add it at the final level. And both are terminated with absorbing layer called perfectly matched layers that then avoid completely the type of reflection. So anyway, again, that can be a full talk in itself. So in the interest of time, I will not go into too many details here. Just to say that there are potential issues that are addressed with some algorithm that is not that simple, but that's what we're going to. And this is recursive, so we can add as many levels as possible ultimately, or as many levels as needed, I should say. So in addition, we're using these spectral solvers. So the reason for this is, so standard finite difference solvers have so-called numerical dispersion, which means that the speed of wave in vacuum, the electromagnetic wave, is not the speed that it should be because of numerical discretization. And this usually is worse as the wavelength is shorter. As of course, the closer the wavelength to the grid cell, then the larger are the approximations. So one way to visualize this is to let a Kronecker pulse being initialized in the center of a grid and just let it go. It should be isotropic and just result in a very sharp front. But because of numerical dispersion, so you see here the effect using a standard finite difference solver of order 4. And you see here, especially along the main axis, how you have this short wavelength that is basically trailing behind the front because of dispersion. So one way to have a better approximation is to use higher order discretization using more points in the finite difference. And you see here going to order 16, order 64, you definitely gain in isotropy. However, it's the numerical dispersion, instead of being subliminal, becomes supraliminal. You see that now the wave that is the shortest wavelength is in front of the actual front. So it's going a bit faster than the speed of light. Now, the way to get even better is to not only be higher order in space, but to be more precise in time. The easiest way is to use shorter time step. Doesn't do much if your stencil is not that high order, but if you go to very high order, eventually you converge toward the very isotropic and sharp front that you should have. However, as you can imagine, if you use a very wide stencil for your finite difference and very small time step here with subcycle by a factor of 10, that becomes very expensive. Well, as it turns out, and that was very well known in the 70s and then kind of became forgotten in the 80s with parallel computers when we switched to finite differences, you can simply integrate your Maxwell's equation in Fourier space. And it turns out that as long as you assume that the source term is constant, which is not shown here, you basically have an analytical solution that is given here. And so you can push your E and M field. You can even have the solution for Kronecker here in one time step. You see that's using this spectral solver in one time step, you have your front. Now, of course, when you use particle, you get time step limit, some type of current condition on the crossing of the particle. So you cannot use this, but at least that gives you a very precise algorithm. And that's very easy to actually implement the equivalent to an arbitrary order. So by default here, because you use K directly, you know, the wave number directly for your derivative, it's equivalent to an infinite order derivative, but you can approximate that with some arbitrary order equivalent K so that you can emulate any finite difference order with a Fourier solver, but the cost is constant, doesn't depend on the order. So, and that can be used, as you will see, to cure the numerical Cherenkov instability. So the way let me just check the chat here. Okay, all right. So the numerical Cherenkov instability was discovered by Brendan Godfrey in the 70s. And it's very simple, actually. If you look at Maxwell numerical dispersion, so omega versus k versus numerical parameters, if you look at the E and M field, the exact is just, you know, a straight line that it goes at the speed of light. And if you assume that you have a plasma that goes close to the speed of light, then they only intersect at 0, and this is stable. Now, if you look at the discretized electromagnetic solver, as we saw now, the wave at the shortest wavelength that would be here, they actually do not go at the speed of light, but at a lower speed. And you see that the dispersion now, the curve is not a straight line, but is distorted like this. And you now have a crossing between the two lines. That means that this is unstable. And that's very similar to the physical Cherenkov instability. It can happen in water, for example, and that's the name for the numerical Cherenkov instability. It's slightly more complex in 2D and 3D. So the equivalent plot here is you see the light cone here, and then the plasma that goes close to the speed of light is represented by a plane now. So you have the wave number along two directions and omega for the vertical axis. And that's the undistorted light propagation on the left. Now on the right, you see that if you have a distorted light propagation, it's not really a cone anymore. So because of the finite difference approximation, then now you have some crossing and it's unstable at the crossing. So you could think that, well, we have a spectral solver that can do the exact solution as on the left. So we have a way to be stable. It's a bit more complex because one has aliases. And the aliases, the way to represent them in that plot is to wrap around basically the plasma. It has this additional plane comes from aliases, and you see that even for the exact light cone on the left, you have crossing and then instabilities. Fortunately, there's an elegant solution that has been proposed by Manuel Kirschen from University of Hamburg and derived analytically by Rémi Lé from Berkeley, which is to take advantage of the analytical solution from the spectral solver to integrate the equation not in a grid that is stationary in the simulation frame, but in a grid that moves with so just a Galilean transformation and follows the plasma. And so again, making the same assumption that I made to derive the pseudo-spectral analytical time domain, the Fourier-based solver, in the static frame, then you get this new algorithm for which things look static and they are therefore stable. And this was, it turns out that it applies not only for a uniform plasma, but it works quite well for plasma acceleration. And you see a demonstration here where the bottom half is from a simulation where we see a wake. So that was driven by a laser, I believe. And you see all this noise, really, that is a manifestation of numerical Cherenkov instability. And you see using the new Galilean PSATD, this is nicely stable on the top half. Now, when people hear about the use of FFT solvers, they are concerned that FFT are hard to scale. If we do the simulation on many cores or many GPUs, as it turns out, because we solve Maxwell, and there's the information between two time step stays into a finite region, and also because we can actually use arbitrary order that is high order but not too high, then the stencil also can be limited in size. Then we can actually use domain decomposition just as with finite difference solvers and do only local FFTs in each of the subdomain for parallel simulation. And that's how we get spectral accuracy, but still scaling that is similar to finite difference. So I'll show some application of the code and this method to the modeling of chains of plasma accelerator stages. So starting a little bit historically with the beginning of the WarpX project that started with coupling MRX with particle incel routines by 2016. By 2017, we did our first modeling of a single plasma accelerator stage with static mesh refinement. And you see a video here that was done by Max and Stephanie of the simulation, laser-driven with a wake. Hard to see, but there is a refinement patch in the middle. And what you see on the left is the emittance versus position of the accelerated beam, and how using a low resolution grid, we get given result. Using a higher resolution grid, we get a better resolution of the beam, and as it turns out, a higher emittance growth in the end. So that indicates we not converge, but regardless, what we showed is that using a coarse grid everywhere, plus a mesh refinement patch around the beam, we were able to recover the result of the simulation with the fine grid everywhere. So that was a nice demonstration of the mesh refinement patch on somewhat short simulation. It was only 100 MeV stage in that case. So going forward in time in 2018, we did pretty much the same exercise, but now at larger scale with the multi-GeV scale plasma accelerator stage. And we also released the code open source to the community at the time. So you see here a result from a simulation beam driven in that case, where instead of using mesh refinement around the witness beam, this time we refined the driver beam. And the figure of merit was to look at the mean energy of the accelerated beam as a function of resolution at the end of the simulation. And what we see is that with mesh refinement, we have this dependency. Without mesh refinement, unfortunately, we didn't go to the last point here. But anyway, but this was already very indicative that the runs with mesh refinement were converging faster, which is what quite nice results. So that basically that indicates that mesh refinement can be used to boost convergence in that case. We then started porting the code to GPUs and started the conversions. Converting the code, which was partly Fortran, to being fully C++, and in the meantime, going to the next level of complexity, which was to not model one stage anymore, but a chain of 3 multi-GeV scale stages. And you see here one example, again using beam-driven, but this time using a refinement patch around the witness beam, and verifying again that, so this time both on the mean energy and on the energy spread, the mesh refined results were converging faster than the similar simulation without mesh refinement. So again, indication that mesh refinement can be used to boost convergence. And then we went to, again, a 3 stages simulation, but laser driven this time. So you see here the setup on the left with, so again, the virtual antenna to inject a new laser at each, the entrance of each stage, and a plasma, a lens. It's supposed to be physically in plasma lens, but it was actually just a radial focusing field that was added here to refocus the electron beam that otherwise basically, just is defocused as it exists each stage and is refocused at the entrance of the next stage. And so that was simulation frame of gamma boost equal 30. And you see the evolution here in the boosted frame, the laser, the wake. You see how the beam expands radially and it's refocused by the focusing lens. And you see the evolution of energy, emittance, and beam width on the right. So again, we varied the resolution to look at the convergence of the algorithm. So we varied it concurrently, transversely, looking at the number of points per beam width, as well as longitudinally with the number of points per laser wavelength across some range, starting from 4 Intel KNL nodes simulations for the lower resolution up to a few thousand of KNL nodes for the highest resolution. And so you see that basically the color and size correspond to the color and size for the curves on the right, looking at the mean energy, relative energy spread, and then projected emittance in X and Y of the witness beam. And you see the dependence versus Z position for each of them. And you see also the dependence with resolution in the insert here. So we really see that we have very nice convergence eventually of these various beam moments for these simulations. So as I mentioned, in the meantime, WarpX was being ported on GPUs, and it uses a portable parallel for C++ structure from MRX, which means that we write the code once, and then it's being compiled automatically for run on CPUs or on GPUs. As I mentioned already, all the Fortran subroutines that were originally reported to C++ and the full PIC loop reside on the GPUs. We transfer the data to CPUs only when needed for IOs. What you see on the right is the scaling as a number of nodes on Summit. So each node has 6 GPUs, and I forgot how many CPUs, a number of CPUs. But anyway, so you see that it has very good scaling for both, basically that, which means close to linear scaling. You see the ideal scaling in green and blue here. This is for a uniform plasma test, as often done for this type of scaling, a warm plasma. And you see that if we used only the CPUs, again, higher is better. So basically that means that we can, forgot to mention, this is the number of particles that are being pushed per nanoseconds. So we can push a lot more particles, as you can see, using the GPUs as we can using the CPUs. And that's assuming 8 particles per cell. So and cubic or the shape factor. So it's definitely dominated by particle these runs. So anyway, using the GPU is very important to be efficient. And having the code running faster on GPUs enabled us to go to the next level, which is the modeling of, the target was 5 to 10 multi-GeV stages, and we went all the way to 10. So it's basically, as you can see, a repeat of the setup for the 3 stages, but with more stages. With, again, laser injection at the front of each stage and plasma lens to refocus between each stage. And you see snapshots here from the simulation with the beam entering in the first stage here, then in the 4th stage, and here the beam being in the 10th stage. And that's the corresponding simulation that you see in the right with the beam going through all the 10 stage and then exiting. Again, we looked at convergence with resolution for the mean energy on the left, and you see the slice emittance of the right. We didn't reach convergence yet, but it's somewhat to be expected as we go through more and more stages. As expected, the beam property kind of diverge, from one simulation to the next. And so the next steps for this, after demonstrating that we can do the simulation, we can go already to fairly high resolution, is to perform ensembles with parametric optimization of each stage, minimizing losses, because in this case, we started to have significant losses along the chain, and also emittance, and assess convergence on ensembles and not just single runs, as was done for the first test here. A few words about in situ data analysis and visualization. So one of the challenges for these simulations, as they become very big, is that there is a very big gap between the computation data bandwidth and the storage data bandwidth. So this is from a slide from Burley-Loring for the computational division in 2017, showing for one computer here how there's basically 5 orders of magnitude in the bandwidth from what we can compute compared to what we can store. So the takeout point for us is that we cannot rely only on data dump to disk with post-processing. There's an increasing need for in situ analysis and visualization. So here's a slide from Axel Hebel that shows basically how we handle in situ data analysis to overcome this IO bottleneck. So WarpX with MRX is represented here on the left, and we use a tool called Conduit that exposes the data to in situ analysis and visualization software. And you see here on the right some of the software that can be used. And with Ascent is a library that basically enable the use of this data that's been exposed by conduit from various tools. One of them is VTKM for visualization, but then you can also expose your data to Python or Jupyter Notebook and do some analysis with them. So we'll show you an example of using this path here for doing some in situ visualization. That means that in that case, the images were created as the simulation was running. And you see this movie here that was done by Axel Hummel. This is the transverse electric field here along the y dimension, which is the vertical axis. You see the beam that is going from one stage to the next. So being defocused and then refocused. We didn't represent the plasma lens yet in this simulation. And this case is not that interested for the physics in a way, but the numerics was such, the resolution is not super high, that we were having a lot of activities in the y direction. And we can see in the movie how we get this burst of particles between stages that are being lost. So this type of movies that can be created at runtime can give us some information that are very useful, as the simulation is ongoing and to look at the end. And would be very costly to do in post-process. So plans beyond this are to go to the modeling of up to 20 stages sometime this year, go then to up to 50 stages by 2022. By then, the exascale computers will start to become available and should enable us to reach our goal to go to up to 100 stages by 2023. And this is in preparation to being able to go to do 100 to thousands of stages for possible collider design around 2030 and beyond. So in summary and outlook, the modeling of plasma accelerators is challenging, especially because of the wide range of space and time scales. The quasi-static approximation and boosted frame solutions have been widely adopted to handle the wide range of time scales in particular. We've been developing a novel called WarpX within the Department of Energy Exascale Computing Project. That includes many advanced algorithms plus built-in GPU support. The modeling of an increasingly long chains of plasma accelerator stages is underway, and we're aiming at hundreds of thousands of stages for collider design down the road. In situ data analysis and visualization is essential to keep up a pace of computation. Looking forward, it's important to realize I didn't discuss too much in details what can go wrong with adaptive mesh refinement, but it's challenging to get adaptive mesh refinement to be robust for simulations, and getting the full benefit is still an active research topic, and that's something that is important for us to know. There's tons of exciting work, so both on the development of adaptive mesh refinement, for example, to do, but also for the application of the plasma accelerators. Thank you very much, and I look forward to your questions.